we're going to talk about evidence of systematic error in your data. So what it looks like if you have systematic errors. Sometimes you can't tell because there's just a shifting of the entire data distribution to away from the true value. And the previous video kind of elaborated on that. But there is some evidence of systematic error in data. There are several different things that you can look for. And again, if you check off all these things, that doesn't mean you don't have any systematic error, but these are good things to check. You may not be looking at very many of these things very often in this lab, but I need you to be aware. So the first thing is model fit, okay? So for example, you may be modeling your data. Most of the models that we'll be using are linear models. But your data may not fit a linear trend. So for example, this data that's given here is clearly not a linear data. It fits a quadratic very well. And if you take the residuals, you can see that those differences are very randomly dispersed around the line. So how you read this plot is that the 0 line is this fit line. Okay, and then each one of these points is a data point in relation to that fit line. So you can see this second point is just above the fit line. The third point is pretty far below the fit line. So here we have a point above and then a point below. So it just tells you how far away are the data points from the line, from the model. And if you have a good model fit, if the model is appropriate for your data, then your residual plot will have your errors or your residuals will look like they're displaced randomly around that line. And that should be the case. That gets to normality and uniform variance, and we'll talk about that in a second. If we fit this data with a linear trend, however, then you'll notice that the residuals look like not randomly distributed, right? They look like there's a trend here, like a parabola. And so this is an indication that the model you have chosen for your data is not appropriate, and that is one form of systematic error. So if you are fitting data that should be linear with a quadratic, then you're going to see that in the residuals. Most likely in our labs, you should have data that is linear, and if you find that it's not linear, then there was some sort of systematic error in your solution prep or in your data collection. The next thing is uniform variance. So here we have you're going to be measuring a lot of masses of pennies. So you've got penny mass as a function of penny number. So penny number 1, penny number 2, penny number 3, etc. Up to 100 pennies here. You're not measuring 100 pennies. Don't worry about that. And their masses. Okay, so we're just plotting what are the masses here. And it looks like this is pretty randomly distributed. If you look at the residuals, this is a little easier to see. These look like almost exactly the same plot. Again, the 0 line is the average line that's here, right? And then this is just going to be the differences on either side. So what this uniform variance means is that the size of the error should be about the same across the measurement range. So at the beginning of my measurement range, I have things that are on this order. What is that, like 0.1 minus 0.1 here? And on the other side of the measurement range, I should also have things that are about 0.1. Okay, and that's exactly what I see in this data. The size of the errors are about the same across the entire measurement range. Now maybe there's an outlier or two here or there, okay, but that's sort of irrelevant. Normality describes that the error should distribute in the shape of a normal curve. So here I have that same penny mass data, and if I look at the residuals and make a histogram from the residuals, then you can see that my errors look like a normal distribution, like a Gaussian distribution around that 0 line. So this data is normally distributed. It has a uniform variance. And just to tie this to what we've been talking about previously, you can see down here the histogram of penny masses also looks like a uniform variance and a normal curve, right? If you plot all of that data, the masses, the penny masses, look to have a normal distribution. If there was some systematic error, this normal distribution wouldn't be symmetric. It would be skewed to one side or the other, And the fewer points that you have, the more likely you're going to see a skewing. But if you collect more and more data, then you should get this normal curve. The last thing is independence. The errors should not be correlated or related to each other in any way. So what this looks like, you can kind of see that this data, there was some data collected over time. You've got a measurement collected over time, and you can see that the data kind of goes up and down and up and down, and it looks like there's some kind of pattern related to this. If you have errors like that, where the error away from the average, right, how far the points are away from the average is a pattern, then that's an indication that there is also some kind of systematic error here. So, to conclude, if you can check these things off of your list and you have an appropriate model fit and you have uniform variance and you have normality and you have independence, okay, then you don't see any evidence of systematic error in your data, but that doesn't mean that you don't have some, right? You could have, if we look at this, this is telling us that our average penny mass is, around 2.5, but maybe the actual penny mass is 2.6, right? Maybe this whole distribution should be shifted over, and we just don't see any evidence of that, okay? So that would be the percent difference that you're looking for. And as in the previous video, really the only way to fix that is to be careful.